Operating system structures. Operating systems offer an environment for program execution and various services beneficial to both programs and users. These services include user interfaces, which are essential for user interaction with the system. Most operating systems feature different types of user interfaces, such as command line interfaces, graphical user interfaces, and batch processing. These interfaces facilitate user commands and program management, enhancing the overall functionality and user experience of the operating system. Operating system services facilitate essential functions such as program execution and I/O operations. For program execution, the system is responsible for loading programs into memory, running them, and managing their termination, whether it concludes normally or encounters an error. Additionally, it handles I/O operations required by running programs, which can involve managing interactions with files or various I/O devices. Operating system services encompass various functionalities, including file system manipulation and communications. File system manipulation involves essential tasks such as reading, writing, creating, deleting files and directories, searching, listing file information, and managing permissions. Communication services enable processes to exchange information either on the same computer or across a network. This communication can be facilitated through shared memory or message passing. Operating system services include error detection, requiring the OS to continually monitor for potential errors in CPU, memory hardware, I/O devices, and user programs. When errors are detected, the OS must take appropriate actions to maintain correct and consistent computing. Additionally, debugging facilities provided by the OS can significantly improve the efficiency of users and programmers in utilizing the system. Operating systems provide essential services to ensure the smooth functioning of the system by managing resource sharing. This includes allocating resources such as CPU cycles, memory, file storage, and I/O devices to multiple users or concurrent jobs. Additionally, operating systems perform accounting tasks to track the utilization of computer resources by users, enabling efficient resource management. Operating system services encompass a range of functionalities, including protection and security measures vital for multi-user or networked computer systems. Protection mechanisms are implemented to regulate access to system resources, ensuring that concurrent processes do not disrupt one another. Security measures extend to safeguarding the system from external threats, necessitating user authentication and protecting external I/O devices from unauthorized access attempts. Operating system services can be illustrated through a block diagram showcasing various components and functionalities. User Operating System Interface, commonly known as the command line interface, is a text-based method for interacting with software and operating systems. Users input single commands into the interface, which prompts the system to execute them and provide a response. The CLI, often implemented in the kernel or by systems programs, serves as a direct command interpreter, facilitating efficient command entry and execution. MS-DOS Command Interpreter was the central command line interface for Microsoft's disk operating system. It enabled users to execute commands, manage files, navigate directories, and run programs directly from the command line, serving as a fundamental tool in early personal computing before the rise of graphical user interfaces. Shell Command Interpreter is a program that interprets and executes user commands, acting as a bridge between users and the operating system through a command line interface. It handles tasks like file management, program execution, and system process control, with popular examples including Bash and PowerShell, each with its unique features. User Operating System Interface, known as Graphical User Interface, which incorporates graphical elements like windows, icons, and buttons for user interaction. GUI interfaces are operated using a mouse, keyboard, and monitor, with icons representing files, programs, and actions, enabling users to execute commands by interacting with these elements. Many operating systems offer both graphical user interface and command line interface options, such as Microsoft Windows and Apple Mac OS X. Unix and Linux systems typically provide a CLI interface with optional GUI options. Touchscreen interfaces have replaced traditional input devices due to the widespread use of touchscreen devices. Users now primarily interact with gestures and virtual keyboards for actions, selections, and text input. highlighting the importance of intuitive and efficient interfaces for enhancing user experience. System calls are vital for programs to interact with the operating system kernel, enabling access to OS services through application program interfaces. Common APIs include Win32 for Windows, POSIX for POSIX-based systems like Unix, Linux, and Mac OS X, and Java API for the JVM. Relationship between an API, system calls, and the operating system can be depicted in a block diagram. Process of system call implementation involves assigning a number to each system call and indexing them in a table within the system call interface. When a call is made, it triggers the corresponding operation in the OS kernel and returns the status and any values. Importantly, callers don't need to understand how the system call is implemented internally. System call parameter passing employs three primary methods: passing parameters in registers, storing parameters in memory blocks with their addresses passed as parameters in registers, and pushing parameters onto the stack by the program for retrieval by the operating system. The simplest approach is passing parameters directly in registers, while alternative methods involve memory blocks or the stack for parameter management. Parameter passing via table block diagram involves a structured method of passing parameters to the operating system. Process control system calls include creating and terminating processes, managing process attributes, memory allocation and deallocation, memory dumping in case of errors, and debugging functionalities like determining bugs and single-step execution. File management system calls involve creating and deleting files, opening and closing files, reading and writing to files, and managing file attributes. Device management system calls include actions such as requesting and releasing devices, reading, writing, and repositioning data, as well as accessing and modifying device attributes. Information maintenance system calls involve tasks like retrieving and setting time, date, and system data, as well as accessing and modifying process, file, or device attributes. System calls are integral components of operating systems, serving various functions like protection and communication. They manage access to resources by controlling permissions, enabling users to grant or restrict access. Additionally, system calls facilitate communication by establishing and terminating connections, as well as sending and receiving messages. Depending on the model employed, such as message passing or shared memory, users can interact with host or process names and create or access memory regions. Windows and Unix operating systems offer a range of system calls to facilitate various functionalities. System programs are essential components of operating systems, facilitating the development and execution of programs. They offer a convenient environment for various tasks, including file management, providing status information, supporting programming languages, loading and executing programs, enabling communications, managing background services, and running application programs. These programs play a crucial role in ensuring smooth operation and user interaction within an operating system environment. File management encompasses various operations such as creating, deleting, copying, renaming, printing, dumping, listing, and manipulating files and directories. Status information retrieval involves requesting system details like date, time, available memory, disk space, and user count, with some tools offering extensive performance, logging, and debugging data. File modification entails utilizing text editors for the creation and alteration of files. Programming language support in computer systems encompasses the provision of compilers, assemblers, debuggers, and interpreters as needed. Program loading and execution involve various tools such as absolute loaders, relocatable loaders, linkage editors, and overlay loaders, along with debugging systems for both higher level and machine languages. Communication functionalities facilitate the establishment of virtual connections among processes, users, and computer systems, enabling activities such as sending messages, browsing web pages, sending emails, logging in remotely, and transferring files between machines. Background services, integral to operating systems, are designed to initiate upon booting and offer various functionalities such as disk examination, process management, error recording, and printing. Application programs, distinct from the OS, are executed by users through command line inputs, mouse clicks, or touchscreen interactions. These programs are not inherently regarded as part of the operating system itself. Internal structures of various operating systems can differ significantly. When designing an OS, it's crucial to begin by outlining clear goals and specifications. These goals can be categorized into two main types: user goals and system goals. User goals focus on ensuring that the OS is convenient, easy to learn, reliable, safe, and fast for end users. On the other hand, system goals emphasize the importance of the OS being easy to design, implement, and maintain, while also being flexible, reliable, error-free, and efficient in its operation. Designing and implementing an operating system involves a crucial principle: separating policy from mechanism. While mechanisms determine the methods of execution, policies dictate the actions to be taken. This approach underscores the creative aspect of specifying and designing an operating system, highlighting it as a highly creative task within software engineering. Operating systems have undergone a transition in implementation languages from early assembly language to system programming languages like ALGOL, and now primarily using a mix of languages including C++ and scripting languages. While assembly is used for low-level components and C for the main body, higher-level languages like Python is employed for system programs. Although higher-level languages facilitate easier portability across hardware, they may result in slower performance, addressed through emulation techniques enabling OS operation on non-native hardware. Different OS architectures include the simple structure seen in MS-DOS, the layered approach exemplified by Unix, the microkernel design as seen in Mac, the modular framework of Linux, and the hybrid system characteristic of Windows. Each architecture offers distinct advantages and trade-offs in terms of performance, flexibility, and maintainability. MS-DOS, developed with the aim of maximizing functionality within minimal space, lacks modular organization. Unix system follows a layered approach, with the hardware forming the bottom layer, layer 0, and the user interface comprising the highest layer, layer n. This design offers the advantage of simplicity in both construction and debugging processes. Unix operating system employs a layered approach, with its functionality constrained by hardware limitations. It comprises two distinct components: systems programs and the kernel. Microkernel system structure, exemplified by Mac, redefines the OS by streamlining the kernel and relocating non-essential components to system and user-level programs. Modular approach in Linux enables the implementation of loadable kernel modules, utilizing an object-oriented methodology where core components operate independently and communicate via defined interfaces. iOS, developed by Apple Inc., stands as a premier mobile operating system tailored exclusively for their devices, including the iPhone and iPad. Android is a mobile operating system initially developed by the Open Handset Alliance, with Google being a primary contributor. It is built upon a modified version of the Linux kernel and incorporates various open-source software. Catering to touchscreen devices like smartphones and tablets. Operating system debugging involves the process of identifying and resolving errors, or bugs, within the operating system. This typically entails analyzing log files that contain error information generated by the OS. Performance tuning involves enhancing system performance by identifying and eliminating bottlenecks. Operating system generation, also known as SYSGEN, involves creating a customized instance of an operating system by merging user-defined preferences and settings with pre-existing manufacturer-provided program code. System boot is the process of starting up a computer's operating system when power is turned on. It begins at a specific memory location within the firmware ROM, which contains the initial boot code. A crucial part of this process is the bootstrap loader, a small piece of code stored in ROM or EEPROM. It locates the kernel, loads it into memory, and starts its execution, allowing the system to transition from being powered off to being operational. Thank you for watching.